We're going to be looking at the first of, I think, 6 lessons in this unit. This unit is called Permutations, Combinations, and the Binomial Theorem. We're not really going to learn what a permutation is and what a combination is until next week, but whatever they are, they're different than each other, but they're very, very closely related. We're going to be solving problems where sometimes it's going to be the most challenging aspect is going to be, am I dealing with a permutation or am I dealing with a combination? Okay. We're also going to be looking at what's called the binomial theorem, and I've got this in brackets on this display because when you first learn about the binomial theorem, it seems to be something really, really unconnected to permutations and combinations. But we will see that it is very connected. When you're solving problems with permutations or combinations, you use very often something called the fundamental counting principle. And that's what we're going to start off with today. So when we learn about the fundamental counting principle, sometimes you will use it to solve permutation problems, sometimes you will use it to solve combination problems. And you can see by some of the images up here that there's going to be some algebra in this, but it's got nothing to do with graphing, nothing to do with functions, very little to do with equations. It has to do with problems that would be, and you'll see lots of them today, but would be problems like how many different ways can you get a royal flush when you're playing poker? Or how many different ways can you roll 2 dice and get an even result? Or if the score at the end of period 2, and this isn't quite the end of period 2, but if the score at the end of period 2 is 5 for the Oilers and 3 for the Flames, then how many different scores might have been possible at the beginning of period 2? It's almost like we're talking about puzzles here. If license plates in Alberta, and this has changed in the past couple of years, but if license plates in Alberta consisted of 3 letters followed by 3 digits, how many different license plates could you have? Or maybe, how many different license plates could you have if you're not allowed to use the letter O and you're not allowed to use the digit 0? Because an O and a 0 might look the same. So some jurisdictions don't allow zeros and O's. Those are the kinds of questions we're dealing with. So today we're looking at the fundamental counting principle. This is actually section 11.1 of your textbook, but I've broken it into 3 parts. 11.1 is called permutations, but we're going to start by looking at what's called the fundamental counting principle. And we have a warm-up that we're going to do to understand it. But basically, at the end of this warm-up, you should understand what the fundamental counting principle is and be able to use it to solve very basic kinds of questions. And we also are going to introduce something called factorial notation. So here's the warm-up. Bobby Bear is planning a vacation. Okay. I took this from, there used to be a website that was animated and it had sounds and it was meant for little children to figure out how to count things. And I'm not using it in a dismissive or I'm not looking down at you and saying you're like elementary children. I think it's a brilliant way to understand the fundamental counting principle. Of course, elementary kids don't call it that. Bobby Bear packs 3 different pairs of pants in his luggage. He's got a blue pair of pants, a red pair of pants, and an orange pair of pants. And he has 2 different shirts, yellow and green. So when he lands at his destination, the question is, how many different outfits does he have? He's got 3 pairs of pants and he has 2 shirts, but how many different outfits are there? And we have to list all of the outfits. Well, there's Bobby Bear. There is 3 pairs of pants, and I do not have his 2 shirts. Oh, that's unfortunate. Give me a minute. Bobby Bear's lost some luggage. Give me a minute and I will get it back. Pants, and there is 2 shirts. And the question is, how many different outfits does he actually have? And clearly you don't need to draw this. What we're going to do is we're going to list the outfits using this notation. I'm going to write pants shirt. And I'll show you what that means in a second. But essentially what we're talking about here is Bobby Bear can wear the green shirt and the red pants. And then what I would say then is that this is RG. That's what I'm talking about in terms of listing them. I could draw it, or I could say red pants, green shirt. Bobby Bear really likes that green shirt. So on the second day of his vacation, he can wear the green shirt with the blue pants. So he's got blue pants and the green shirt. He can continue to wear that green shirt because he has a third pair of pants. And I think it's kind of important that you understand at this point in time, if he wants to wear a different outfit every day, then he's done with the green shirt. Because he's worn that green shirt with all of the different pairs of pants. So this would be, what are we talking about? An orange pair of pants and a green shirt. We can continue. He can look at wearing the yellow shirt now with the red pants. And I think some of you will be catching on to this, that there's going to be 3 more outfits. Because for the yellow shirt, he has 3 different pairs of pants he can wear. This would be red pants and yellow. And this is not, I hope you appreciate, this is not how we're going to solve these problems, right? There's got to be a better way. Yellow shirt again. Blue pants. And then he can wear the yellow shirt again with the orange. Oh, who wears yellow and orange? I better be careful. No, we're okay. Didn't insult anybody. So what we have here then is blue, yellow, and orange, yellow. So there's 6. And I hope it makes sense to you that no matter what you try to do here, you're not going to get a different outfit. I wish the website was still up, because you know, if you tried to drag over the same outfit, there'd be this voice that calmly said, oops, you've already made that outfit. And it's intended for children, but the answer to this question is 6. And there's some fundamental math 30 involved in this. So the answer is 6. That's how many outfits there are. Now, when we get to more complicated problems, like this one, let's read through it together. First of all, there's a little ice cream stand somewhere. It's just a little tiny place. And it's just a tiny little outfit, maybe just a little stand on a beach. And they have 2 different types of cones. They have regular ice cream cones, and then they have what's called a waffle cone. They only have 3 types of ice cream. They have strawberry, vanilla, and pistachio, because the ice cream vendor has a severe allergy to chocolate, I guess. I don't know, but those are the 3 flavors. And there's 2 different types of sprinkles. And it says a single ice cream dessert. So you go and you buy an ice cream. You have to have a cone, you have to have ice cream, and you have to have sprinkles. Okay, we'll talk about what happens later in a few minutes if you don't want sprinkles, okay? How many different ice cream packages could I get? So I don't think I want to draw a regular cone with vanilla ice cream and mint sprinkles, and then draw a regular cone with vanilla ice cream and, oh, there is chocolate sprinkles. Do you see how easy it would be to lose track of what you've already counted? So we're going to use what's called a tree diagram. And the first step in the tree diagram is a choice that you make. And this lesson today is all about choices, everybody. Bobby Bear had to choose a shirt and choose a pair of pants. Here you have to choose a cone, you have to choose a flavor of ice cream, and you have to choose a type of sprinkle. So we put our first options for the first choice here, and then we say, have you noticed I'm using bold here for the different choices? If you choose a regular cone, and you know, think of the vendor standing there. She's got a regular cone in her hand. She says, okay, now what kind of ice cream do you want? This choice branches off, because you can then have the regular cone with strawberry, or the regular cone with vanilla, or the regular cone with pistachio. On the other hand, if you chose a waffle cone, you have the same three options. And I want you to listen very carefully to this next bit of business. So far, there are 6 options up here. If I count how many items are in the lowest level of my tree diagram, that's how many options there are. Regular with strawberry, regular with vanilla, regular with pistachio, that's 3. Waffle with strawberry, waffle with vanilla, waffle with pistachio, I'm at 6. But let's assume that one customer says, I want regular and I want strawberry ice cream. She now looks at that customer and says, well, okay, well, what kind of sprinkles do you have? So there's another choice. And the regular strawberry branches off now into 2 things. Regular strawberry chocolate sprinkles, regular strawberry mint sprinkles. And we continue in this fashion. And although you do need to be able to draw tree diagrams and understand them, this is still not the most efficient way of doing this problem. There's a simpler way. Each of these branches off. And each of these will branch off as well. So that's what your completed tree diagram is going to look like. And if you ask yourself how many options are there, every item at the bottom of the tree diagram is one option. So when I look at this, it's not just chocolate sprinkles. It's a regular cone with strawberry ice cream and chocolate sprinkles. There's 1. There's 2. There's 3. There's 4. And I hope you see that if you start drawing all this in, you're making it more complicated and confusing than it needs to be. You count the number of items there are on the bottom. And since there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 items, there are 12 different packages of ice cream that you can get here. The answer is 12. The next example is going to illustrate why we really need a better method than a tree diagram or trying to write them all down. Because number 3 is really the same as number 2, except there's more choices. You still have 3 decisions to make. This is a car rental company. They have minivans, compact cars, and hybrid vehicles to rent. They only stock 3 colors, black, red, and hot pink. And you can get an automatic or a standard transmission for all of the vehicles. The question is, how many different vehicles are there? Well, we do a tree diagram. You can have a minivan, a compact car, or a hybrid. Now you have another decision. Again, this is all about decisions today. You have another decision to make, which is, okay, if you have a minivan, what color do you want? Well, you can have black, or you can have red, or you can have hot pink. And I've drawn it that way because each of these is going to branch off again. So I just need a little bit more room. Okay. If I drew them so that those 3 letters were all on the same level, then my font would have to be getting smaller and smaller and smaller and smaller as I went down. But for each of these models, minivan, compact, or hybrid, you have 3 colors. So if you didn't have a choice of transmission, the answer to this question would be 9 vehicles. Minivan black, minivan red, minivan pink, compact black, compact red, compact pink, hybrid red, hybrid black, hybrid pink. But each of these branches off into standard and automatic. So that S and A there means 2 options. Minivan that's black with a standard transmission, minivan that's black with an automatic transmission. And then we continue doing this. This is not what you thought you signed up for when you enrolled in Math 30-1, right? But we add that standard and automatic to everything. And then we count the number of items at the lowest level of the tree diagram, which is going to be 18. I'm not going to highlight all of them, but here is one option. Here is another option. Here is a third option. Whoops. We'll do this. Here is a third option. Here is a fourth option. Fifth, sixth. There's 6 there, 6 here, 6 there. It's 18. The answer to this question is 18. Okay, so now let's talk about the fundamental counting principle. The fundamental counting principle says this. If you have I'm going to explain it in my own words. If you have a series of decisions that all need to be made, like picking out a shirt and a pair of pants, like choosing a cone, ice cream, and sprinkles, whatever. If you have this big job that is composed of all of these other pieces and you need to make a decision for all of them, then the number of ways you can do the big job is found by multiplying the number of ways you could do each of the pieces. So if I have some complex task that's composed of choosing something, and I'm going to call that choice A for the first stage, and B for the second, and C for the third, if those are how many ways I can decide, then I multiply those things together to get the answer to the problem. How many ways I can do the task. Let me show this to you now. Oh, by the way, I really want to highlight this. And I don't believe I put this in your notes. I printed it out after I decided to put this. I really want you to note that the fundamental counting principle is basically saying the word and means to multiply. It's a very important idea in this unit. Bobby Bear needs to wear a pair of pants and a shirt. Okay? You need to choose a cone and an ice cream and a sprinkle. You need to choose a model and a color and a transmission. So, if you look at Bobby Bear's problem, if he has to wear a pair of pants and a shirt, you can take the number of pairs of pants times the number of shirts and get the number of outfits. It's that simple. We didn't need to draw all of these different things. How many cones did you have in this example in the warm-up? Well, there were 2 cones, there were 3 flavors of ice cream, and there were 2 sprinkles. What's 2 times 3 times 2? It's 12. Didn't we get 12 different ice creams? Are you with me on this? Okay. We had 3 models, 3 colors. I'm not sure. Some of my stuff is being sucked into the vortex somewhere. And 2 transmissions. If you multiply 3 times 3 times 2, you get 18. Now, I had told you I wanted to show you what would happen, and this is, I guess you can add it as an example. You don't have to write it down, but what would happen if you go to this ice cream stand that says $5. Choose your cone, choose an ice cream, and you can have sprinkles if you want. Then how many different options for cones would there be? Well, there would be 2, right? There's 2 cones. How many different options for ice cream would there be? 3. How many different options would there be for sprinkles? Marcel? It'd be 3. Because you can have chocolate sprinkles, or you can have mint sprinkles, or you can have no sprinkles. Picking 0 sprinkles is an option, so it's a choice. And the answer to this would be 18. You know, if the answer was you don't even have to have ice cream, then it would be 2 times 4 times 3. I don't understand the purpose of that. But all right, let's take a look now at some problems. And as many examples that we're going to do together, there are thousands of different examples. It just has to be something you get used to thinking about. If I take all of the letters from the word reason and I arrange them, okay, I want to draw your attention to the fact that arrangement means ordering stuff. What that means, and you're going to wonder why I'm talking about this, but you'll see later why it's important, is that when I arrange these, if I put the S there, I can't put the S anywhere else, right? I can't use the S over and over again. I'm physically taking these things, and that's why I have Scrabble tiles up here. I'm physically taking them and arranging them. Now, if the arrangement must start with an S, and you should draw 6 blanks in your solution here. If the arrangement starts with an S, then we're going to write below this first blank, must be an S. And I want you to note that you have 6 decisions to make. You don't have 2 decisions. You're not picking out a shirt and a pair of pants. You don't have 3. You're not renting the vehicle. You have 6 decisions. You have to decide to put something in the first blank, the second blank, the third blank, the fourth blank, the fifth blank, and the sixth blank. Which means that above these lines, I'm going to write down how many choices we have for each of these, and the fundamental counting principle will say I'm going to multiply all those numbers together. But here is something that you have to understand from the beginning. This is called a restriction. And when you apply the fundamental counting principle, you take care of the restrictions first. So we don't put any numbers above any of the other blanks until we've filled in the restrictions. So if the first blank must be an S, how many S's do I have to choose from? 1, right? And then I have to make decisions on the other blanks. Now you can decide on them in any order you like, but I like working in an organized way from left to right. Arden, how many different letters can I choose from to put a letter in the second blank? 5. Because I've already chosen the S, right? So this is 5. And then how many do I have to choose from for the next blank? 4. It's that simple. Because each time I put a letter in there, I don't know what letter I've put there, but I know that there's 1 fewer to pick from. So this will be 4, and then I'll have 3 left, and 2 and 1. I want you to notice, if you willy-nilly just put them wherever, you would still have the same numbers. If I said, how many can I put here? 5. How many can I put here? 4. I want to be careful. It's not that I can put 4 there. That's not what I mean. How many do I have to choose 1 from to put there? And, you know, I could put the 3 here and the 2 there and the 1 there. I don't like that. I like going left to right. So the answer is 5 times 4 times 3 times 2 times 1, which I believe is 120. Okay, so there are 120 arrangements of those letters. If the first letter didn't have to be an S, then we would put the following numbers in the blanks. 6 times 5 times 4 times 3 times 2 times 1. Number 2, we've got a class with 25 desks, and as it turns out, exactly 25 students. It's day 1 of the class. How many different ways can the students be seated? How many different ways could they pick where they're going to sit for this semester? Well, this is a little bit weird to think about, but we have to think about it somehow that's going to work with the fundamental counting principle. And I would say the best thing to do is just say, you're going to stand at the door and you're going to allow them in one at a time and allow them to sit wherever they like. So the first person that comes in, how many different desks can they choose from to sit at? 25, right? Now they may not choose to sit there, but there are 25 choices. And I'll show you a different way from a teacher standpoint this makes sense. Okay, so there's somebody sitting there, there's 24 empty desks, which means, and my goodness, don't write this all down and don't calculate it either, okay? If you know where this is going. Just pay attention up here, please. The next student is going to have 24 choices, and then 23, and then 22. And you're going to multiply these all together until you get to this. Now there's another way that makes sense, and it might make more sense to you, I don't know. It does to me. As a teacher, I've got my list of 25 students, and I'm going to put them in desks. And I look at my seating plan, and I look at this desk here, and I have to pick a student. How many different students can I choose from? 25. And I cross their name off the list. And then I have to seat somebody here. I look at my list, I only have 24. The bottom line is, this is the answer to the question. And if you do that, you get 1.55 times 10 to the 25. And that's a very big number. We don't know what the decimals are. I put it into Excel, where I can say, show me all the decimals, and I get this number. But I wouldn't even know how to begin to say that number out loud, other than 1.55 times 10 to the 25. So we abbreviate it this way. And it's not 25. It's not that. It's 25 factorial. That's how we pronounce it. That exclamation point in math means take that number and multiply by one less and multiply by one less and keep going down until you get 1. I am perfectly aware, as you should be, that you don't really need to write times 1. It doesn't change the value. Okay? On your calculator, you can find the factorial function in your math menu. You hit the math key and it's in the probability submenu, the far right menu. You can just scroll to the left to get there if you like, and there's the exclamation point. So you would enter 25, navigate to that place, 25 factorial. Okay. All right. Number 3, all of the letters of the word diploma are used. How many arrangements are possible that begin and end with an I, O, or A, the vowels? So this must be an I, an O, or an A. This must be an I, an O, or an A. And we've got a total of 7 blanks, 2, 4, 6, 7, because we are arranging 7 letters. So I have to do my restrictions first. I have 3 items to choose from to fill in that first blank, which has a restriction. Marcel, how many options do I have to fill in the last blank? 2, good. Because I don't know which of those 3 vowels I've put in the first blank, but I know I put one of them there. And at this point, now I can start populating the rest of this. In other words, I've made 2 decisions. I have 5 more decisions to make. And remember, these decisions are going to be multiplied together. Jonathan, how many choices do I have to fill in the next blank, wherever it is? Yes. It's not about the numbers I put up top. It's about how many numbers I put up top, right? I've filled in 2 blanks. So out of the 7 letters, I have 5 left. So this will be 5, and then times 4, times 3, times 2, times 1. And this is going to work out to, you can confirm this please, 720. Okay. Now, on an exam, a multiple choice exam, or maybe even a numerical response exam, I'll stick with multiple choice, you might be told the answer is 6 factorial. Now just confirm that 6 factorial is 720, first of all. And by the way, I hope everybody here knows 5 squared is 25. Sooner or later, you will know your factorials up to about at least 5 or 6 or 7. But why is it 6 factorial? I want you to notice that this multiplied by this is 6. And we have 6 times 5 times 4 times 3 times 2 times 1, so it's 6 factorial. It's not 6 factorial because you're arranging 6 letters or anything. It just happens to be 6 factorial. A volleyball team is made up of 8 players, and they're going to stand in line facing a camera. Just before we begin, putting those players in a line is no different than putting those letters in a line. This is something you're going to have to get used to in this unit, is you will look at this question and you will look at a apparently different question, but it's really the same idea. They have to stand in a line, but Joan and Emily have to stand together. And the question is, how many ways can you arrange them? So here they are. Here are the 8 players. And you're not going to draw these, but there are the 8 players. And you can see Joan and Emily at the bottom there. There are 8 players, but we're not going to arrange 8 items, because Joan and Emily have to be together. We only actually are arranging 1, 2, 3, 4, 5, 6. We're actually arranging 7 things. Okay? So when we solve this problem, I'm going to have 7 blanks. 1, 2, 3, 4, 5, 6, 7. And I have to decide which of these 7 items, and one of the items is a group of 2 people. I have to decide which of these items goes in the first spot, and that would be 7 choices. And I've chosen some item. Maybe Patty is there, maybe Sam is there, maybe Emily and Joan are there. But remember, they're together. Okay? And then I have 6 left, and 5, and 4, and 3, and 2. And then whoever I haven't chosen goes last. And I don't know what that is. Is it 50-40? It is 50-40. 7 factorial is 50-40. But that's not the answer. And I want you to try to figure out why it's not the answer, or what the correct answer is. There's nothing wrong with my logic. It's just that we have to do something else. You have one more decision to make. You have to decide which of these 7 goes in the first, which of the remaining 6 goes in the next, etc. But then at the end, you have one more decision to make. Marcel? Whether Emily is on the left or right. Right. We have to arrange Joan and Emily. So we also have to multiply by the number of ways to arrange Joan and Emily, which is easy. It's 2, right? But I want you to understand something here, because it will not always be easy, that we're multiplying by this for Joan and Emily. I know you know that there are 2 ways for them to stand. Okay, so you could just multiply by 2. The bottom line here is, when you do that 7 factorial to get 50-40, that's how many ways they can be arranged if Joan is on the left. But these are different. Whoops. Yeah, these are different. Look where Joan and Emily are. They're in the same place in both of these, but they've swapped sides. So the answer is 7 factorial times 2 factorial. You understand 2 factorial is 2? 2 times 1? I hope you understand 3 factorial is not 3. It's 3 times 2 times 1. Anyway, 10,080, is that a number that works? 10,080. Did I write that down correctly? Thank you. All right. Janice, Becky, and Sophia must be together. Okay, if Janice, Becky, and Sophia must be together, then this is what's going on. Right? Now, do Janice, Becky, and Sophia have to be holding hands in that order? No. We'll get to that in a bit. But what I'm going to arrange is 1, 2, 3, 4, 5, 6 items. Now, can we at times stop writing blanks? Can't we just write 6 factorial? If I want to arrange these 6 items, I could put 6 blanks and then go 6 times 5 times 4 times 3 times 2 times 1. I'm only going to do that so many times before I pick up on the fact that when I'm arranging a number of items, as long as there's no restrictions like somebody has to be at the beginning, the answer is the number factorial. But I also have to multiply by the number of ways to arrange Janice, Becky, and Sophia, which is not as simple as just saying 2, right? Like with Joan and Emily. This is 3 factorial. And I'll get to the answer in a second, everybody, but I think as soon as you go from this, 1, 2, 3, 4, 5, 6, and then you have to go times 1, 2, 3, as soon as you go from that to this, it makes the thinking clearer in my mind. Those blanks are starting to get cumbersome and confusing. It's 6 factorial times 3 factorial, which is 720 times 6, which I have no idea. Have you got a number, Madison? 4320? Okay. And by the way, these are not always questions on exams that we want a number for an answer. It could be that you're given this question and told it can be written this way. What are the 2 values of A and B? All right, now the one that requires today maybe the most thought. Patty and Alice cannot stand each other. They cannot stand next to each other. And there's only one way that I would recommend doing this. Let's first of all find how many ways, how many arrangements of everyone are there? If you had to arrange all 8 players in a row, figure out for me how many arrangements there are. Forget about Patty and Alice and their grievance with each other. How many ways can all 8 stand together in a line? Sorry, Shazmina. I'm back now. Somebody was at the door I had to talk to for a second. Well, do you see that fundamentally this is the same as the first question here with Joan and Emily? Wasn't it 10,080? So it was 7 factorial. I mean, Alice and Patty are treated as one individual, so now we're arranging 7 items instead of 8, and then times 2 factorial. So I would like you now to appreciate something that's fundamental to solving this problem. There's only 2 possibilities with regards to Patty and Alice. They are either going to be standing next to each other or not. So the way I like to explain this is, whatever 8 factorial is, let's erase. 40320? 40320. Imagine that I have no life, and sometimes that's not a real stretch of the imagination, and I decide to get 40,320 index cards, and I write down the order of each of these arrangements on each card. Okay? So I've got this big table full of cards and I'm carrying them, whatever. And I look at the card. Actually, what I do, I go into the gym and I put them all down on the floor. Okay? Face up so I can see them. And I start walking up and down the rows. And if Patty and Alice are together, I flip the card over so I can't see it. I turn over all the cards where Patty and Alice are together. Or I take all the cards with Patty and Alice together and I throw them out. What am I going to be left with? I'm going to be left with the cards where they're not together. So in order for me to find out how many arrangements do we have where they're not together, I can take the total number of arrangements minus the number of arrangements where they are together. And again, we can do a numerical answer, but that's not the point. It could be a factorial minus b factorial c factorial. This was this the 10,080? Is that my memory right? So we're going to subtract those two and get 30,240. I've had lots of clever students over the years, and some of them want to try to figure out how to get this number directly, and they put the blanks, and then they start, putting Patty in one blank, and then figuring out, but Alice can't be next or before. It's confusing. It's impossible. It might be easier if you had only 4 or 5 people, but 8 is difficult. All right. Let's do a few more. Consider the letters of the word English. How many different 4-letter arrangements can be formed if letters can be repeated? So, first of all, we have 7 letters, and we're only arranging them in groups of 4. That's different. And you can use the same letter again. So I have a bucket of E's, a bucket of N's. In other words, I can do this. I have as many of those letters as I want. I'm still going to use the fundamental counting principle. I'm just going to say that there are 7 choices for the first blank. How many choices do I have, or how many items do I have to choose from for the next blank? Seven. And the next 7, and the next 7. So this is 7 raised to the 4. Whatever it is, I don't really care. Okay. If you want to know the number, you'd work it out. What about now? No letters can be repeated. So if you look up here, the idea is now if I put an S here, the S is gone. I cannot repeat. No letters can be repeated. Well, this would be 7 times 6 times 5 times 4. Right? And then 3 of the letters don't get chosen for each particular arrangement. And I hope you'll forgive me that sometimes I don't put the multiplication symbols in. I mean, we know the fundamental counting principle says you multiply. So 7 times 6 times 5 times 4, I want to say 840. Good. So there are 840. Continuing with part B, where we cannot repeat letters, what if the first letter must be an E? Well, this has to be an E. And then this, it's not, all right, who cares? It's not that we don't care, it's that it doesn't matter. That's my point. So there's one E multiplied by how many different choices or how many different items can I choose from for the next? Well, I've got 6 letters left, and then 5, and then 4, which is 120, which is 5 factorial. 5 factorial happens to be 120. Just the fact that you know, if you see the answer is 5 factorial, don't say, wow, where did the 5 come from? Because there's 7 letters. It's just a fluke. It can be abbreviated as 5 factorial. I do this one a different way in my head. I say if the first letter must be an E, then the question is really, how many 3-letter arrangements can I make from these letters? You're not even allowing me to participate in the first blank, so I'm not even going to waste time thinking about it. It's 6 times 5 times 4. Multiple choice exam has 35 questions, each with 4 choices. How many different sets of answers are there? So I could build my test and have every answer being A. That's one option. I could go A, B, C, D, A, B, C, D, A, B, C, D. I could go A, B, B, B. Like if I ran through all of the arrangements, how many would there be? I don't want to write 35 blanks. There are 4 choices for the answer to the first question, times 4 choices for the answer to the second, times 4 choices for the third, etc., 35 times. And don't try to figure out what 4 to the 35 is. It's probably some astronomical number. It may even go beyond the memory of your calculator. I don't know. The answer is 4 to the 35. After saying that, I'm curious. Yeah, I mean, that scientific notation is handy, but in terms of a number of things, all we would say is that it's really big, isn't it? Really big. Car plates in a certain country, so these questions are getting progressively more complicated because there's more information you need to pull out of the words. License plates in a certain country consist of a letter other than an I or an O. So this is not I, not O. But it's a letter. Followed by 3 digits. So these are the 3 digits here. The first of which cannot be 0. Do you see why some of these questions would say you can't use an O, you can't use a 0? They look the same. And I's with some fonts, an I looks like the number 1. I want to be careful here. It says, followed by 3 digits, the first of which cannot be 0. It doesn't tell me anything else about those remaining digits, so I'm allowed to use the same digits over and over again. That's the default position, is if you're not told with numbers, you can use the numbers again. By the way, could you imagine a license plate with 2 followed by 2? It's possible, right? Common sense says you have to be able to repeat. And then what? Followed by any 2 letters. So these are 2 letters. These are 2 different letters. They are different from each other. So, I mean, you do need to know something. You do need to understand in the English alphabet there are 26 letters. You do need to understand in the mathematics system we've adopted there are 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1 through 9 and 0. So this would be 24. This would be 9. This would be 10. This would be 10. This would be 26. This would be 25. Whatever that multiplies to give is the answer to the question. Let's say 14 million something. 141 million no, that's not right. I've got a space that's missing here. Come on. Yeah, 14,040,000. By the way, I said about 14 million. It's not because I worked it out. I just almost stranger. I remembered the number from last time. It's around 14 million. 14,040,000. Any questions with that example? All right. Consider a 6-digit numeral. So first of all, a numeral is a group of digits forming a number. But if I wrote down 0, 2, 4, 3, 5, 6, that is not a 6-digit numeral because we don't need to write the 0. In other words, if I want to create a 6-digit numeral, this cannot be 0. Because if it is 0, it's a 5-digit numeral. Okay. How many odd 6-digit numerals are there? Okay, so if you have a numeral that's odd, like 625 is odd, 624 is not, this must be an odd digit. And we're not allowed in this question to repeat the digits. So we do this restriction first. There are 5 options here. And I'm putting the number 5 there not because 5 is an odd number, but because there are 5 odd numbers to choose from. Now let's do the next restriction. It cannot be a 0, so wait a minute. Of the 10 digits in this box, I've already used one of them here, right? So I'm down to 9 digits left in my pool to choose from. But of those 9 digits, 0 is in the pool, which means this is actually 8. So let me run that logic through you again, through your brain. We only have 5 odd digits to choose from, so we have 1 of 5 here. That's a fact. If I want to do the beginning digit now, which is another restriction, I have to put in a digit that's left that I haven't used because I can't repeat. I have to put a digit that's left but not a 0. So one of these has been swallowed up by the final blank in our 6-digit numeral. So we're down to 9 digits in total, but I can't use the 0 in the beginning, so that's 8. How many digits can I choose from for the next blank? Isaiah, what do you think?
8.
It is 8. Because I've used an odd digit at the end, that's 1 gone. I've used another digit that's not 0 at the beginning, that's a second one that's gone. Whatever has happened, I have 8 left in the pool, and then I have 7 and 6 and 5. So if we multiply these out, we're going to get the answer. $67,200. So I want to talk to you about something here that's really important. This first line is the fundamental counting principle. It is what we've been doing all along. But there's another rule in math, and you'll have to take my word for it. It will become clearer why it works. But the word or in math means add. Okay? And means multiply, or means add. And at times it's useful to remember that because it makes our job easier. So the next question has a rational function that is x minus 9, x minus 3 over x minus 8 x minus a rather, x minus b. And what you were, as students, are allowed to do is pick any of these 10 digits for a or b. You can put 3 in for a and 3 in for b. You can put 7 in for a and 0 in for b. You can do whatever you want. But what we're interested in are the rational functions that have one whole and one vertical asymptote. So what are the options here? If I have this function, y equals x minus 9, x minus 3, over x minus a, x minus b. If I have one whole and one asymptote, the whole can be at 9, or the whole can be at 3. Because a whole results from having a factor that cancels on the top and the bottom. So if I have a whole at 9, that means one of these has to be a 9. Okay? So what we're going to do here is have a and b. We have to choose something for a and something for b to get a whole at x equals 3. We're going to do a and b. This is a and this is b for a whole at 9. And we have to choose a and b for each of these, but we don't do both of them. The whole is at 3 or the whole is at 9. So we're going to find out how many rational functions we can create with the whole at 3, and we're going to find out how many we create at 9 and add them together, because that would be how many would have one whole. There's a little bit more involved, but let's do the whole at 3 first of all. Well, that would mean that we have to pick the number 3 for, I'm just going to say a. I hope you appreciate that where a minus b and a minus a are, it doesn't matter order-wise. So if I want the whole at 3, a is 3, which will give me an x minus 3 here, which will cancel. How many different numbers could I choose for b? I can't choose a 3, can I? Because if I choose a 3 for b, that means I don't get an asymptote. I need an asymptote. I need a different factor that doesn't cancel with something on the top. So I can't use a 3. What other number could I not use for b? Martin, do you know? I can't use a 9, because if I use a 9, I have 2 holes. So that means this is 8. This is anything except for a 3 and a 9. I can use any digit I want except for a 3 and a 9. If I do the same thing over here and I say that this is a 9, this cannot be a 3 or a 9 for the same reasons, so I'm still going to have 1 times 8. So 1 times 8 plus 1 times 8 is 8 plus 8, which is 16. There are 16 different rational functions we could create here. And I believe we have one last question. In how many ways can 3 physics books, 4 chemistry books, and 5 bio books be put on a shelf? So I'm going to put these, what do I have? 7, 12 books on a shelf. I'm going to arrange them. But I'm kind of a weird guy. I want my physics books together, and I want my chem books together, and want my bio books together. So I guess the number of ways to arrange the physics books, this is arranging the physics books, would be 3 factorial. I need to multiply that by 4 factorial. This is arranging the chem books. And I need to multiply by 5 factorial, which is arranging. I don't know that you need to write all of this down. I'm just doing it because arranging the bio books, that's not going to be the answer. It's all about decisions. I take out these 12 books, I put them on the floor, and I look at my bookcase, and I'm going to make decisions as to where everything goes. I've made the decision as to how to order the physics books. I've made the decision as to how to order the chem books. And I've arranged or made the decision on how to arrange the bio books. What other decision needs to be made? Jonathan? Sure. Or just to make it even more general, because it could be 3 shelves or it could just be in a row, I have to decide the order of the topics. I have to arrange physics, bio, and chem. I could put, if you're thinking shelves, physics on the bottom, then bio, then chem. I could go physics, then chem, then bio. So I need to multiply by a further 3 factorial, which is arranging the subjects of physics, chem, and bio. Arranging the groups of books. I don't know what that's going to give you. 36 times, I don't know. I want to say 103,680. 103,680. Now, as many of these examples that we've gone through, there's just tons more of problems. You are going to have to make a lot of choices, speaking of choices in this unit, as to what you want to put into it. I have 14 questions in one section, 14 questions in another section. The first section deals essentially with the fundamental counting principle. I would describe this as being very basic. I have this from an old resource, so sweaters and slacks, okay. Skirts. And then the second section, I think, just gets into more restrictions. So how many ways can Bobby Bear get dressed, different Bobby Bear, so that he doesn't wear his white belt with his red pants, okay? Whatever the case is. And you have to try to exclude those. So that's what you're working on for the remainder of the class and getting ready for Monday when we continue with this.